like to start this session by welcoming Kat Morris, who's from my team, who will be talking about experiences improving our legacy calibration process.
So hello and welcome. So I'm Katherine Morris, an engineer in the Radar Research and Development Department here at the Met Office. And today I'm going to be talking to you about our experiences with improving the standard legacy calibration process. So just as a brief overview, so I'm going to cover the background of the Met Office's radar network, describe what a standard legacy calibration is and why we do it, and then I'll move on to our motivations for improving the process and the improvements that we've made. I'll finish up with some of the challenges that we had and any further work. So the Met Office has a network of 15 operational C-band dual polarization radars, and these are an in-house development. So that includes both the hardware and the software. So one part of our software is Cyclops, which is our radar processing and control system. Cyclops has been developed to be cross-platform. So, for example, our operational servers are in Windows, but we do a lot of our development work in Linux. And it's also been developed with a microservices architecture. So if I draw your attention to the top right, so this is an example of a monolithic application. So this is where you have one large application that does several different tasks and everything's very tightly coupled and difficult to separate. So in contrast, what we've done with Cyclops is using a microservices architecture. So this means that we separate one larger application down into independent services, each that have got their own tasks and responsibilities, and then they communicate between each other by passing messages. So this has a lot of benefits. So for one, it's a lot more flexible. It means that we don't need to run the entire application every time. We only need to run the services that are appropriate for the task. And then it also means that this is language agnostic. So this is just a couple of examples. This isn't an exhaustive list of all the services in Cyclops, but you can see that any of the services that require real-time processing have been developed in C++, whereas some of the services that are less time critical have been developed in Python. So the reason that this is important for the standard legacy calibration is that this, so receiver calibration GUI, so this is the standard legacy calibration service that we'll be discussing from now on. So the purpose of a standard legacy calibration is to calculate the losses in the receiver so that we can calculate a calibration factor that's used when converting from a received power to a reflectivity. So this is important because we produce composite products and also contribute towards European products. So it's important that the reflectivities are consistent across multiple sites. It's important to note, so our radars do not have an internal test signal generator. So the way that we do this standard legacy calibration is that we connect an external, well-calibrated test signal generator. We inject a known power and then measure the output power at the analog to digital converter in the receiver. This is repeated across the dynamic range, and from there we can calculate a calibration factor. So this is typically performed every 6 months during routine maintenance, and then additionally also after the replacement of any receiver components. So the motivation to improve the standard legacy calibration process was that we had quite a significant server upgrade. So we went from a 32-bit server to a 64-bit server, and this required the rework of some of our existing applications. So we took the opportunity to improve upon the process wherever possible, and also to leave the door open for any future improvements. So the old process was spreadsheet based. So our field service engineers would connect up the signal generator and set it to the correct parameters. And then they would read off the power values and then manually type them into this spreadsheet. The spreadsheet would do some of the any of the calculations required. It would plot the graphs, and it would do some basic verification. So there are obviously some disadvantages to this sort of process. So for one, it was very time consuming, and due to the amount of manual data entry, that meant that there was the potential for errors. We're also restricted to doing the calibration at a nominal frequency rather than the actual frequency of our transmitter at that site. And then this process is also just very rigid and difficult to improve upon. So the new process is a graphical user interface, or a GUI, and this has been developed using the GUI framework tkinter, which is part of the Python standard library. And then additional dependencies are NumPy, that's used for any of the calculations, and optionally matplotlib, which is used to plot any of the graphs. So we still do need to set up the test signal generator with the correct parameters. But after that, the engineers can select the appropriate row in the table and then click the Get button, and that will interface with the analog to digital converter in the receiver, and it will automatically make any of the measurements that it needs and store these powers in the table. So there are obvious advantages to this type of process. So first of all, there's no manual data entry required with this, and it's also been reported to be 4 times faster than the previous process. It's also a lot more flexible, and it's been designed in a way to make it easy to do further improvements. So we do some verification within here on some individual values. So we do verification on the differential gain and cross-channel isolation. So you can see here, this is an example where it's failed that verification. And then we also do verification as a bulk check of all values. So that's done on the differential gain, the linearity, the sensitivity, and the cross-channel isolation. So this is intended as a Boolean pass or fail, and that will indicate to our field service engineers as to whether they need to do any further investigations and indicate where to start troubleshooting. These thresholds for the verification are also configurable. So that's something that we hope to do in future, narrow that down to make sure that the verification is only failing when action is required. So with the time saved, we've been able to implement an additional calibration by default. So we'll be doing this additional calibration that will sample a different path. So in a typical calibration, the power is injected and then it travels through a run of waveguide, the TR cell, and then the receiver, where it's measured at the analog to digital converter. This additional calibration will be injecting the power directly into the receiver and then measuring the power at the ADC in the receiver. So we'll be able to compare these two calibrations and isolate whether the signal loss is coming due to a degradation of receiver components or whether it's due to a degradation of the waveguide or TR cell. So we're hoping that this will give us the opportunity to do long-term monitoring and get advanced warning of any waveguide corrosion or issues of the TR cell. So the plan is that we can then do predictive maintenance to take action before we reach the point of failure. So any of the site-specific calibration factors are stored in Git, which is a version control system. and this gives us full traceability as to exactly what changes have been applied. And then additionally, any changes are associated with a commit message, which gives us further context. So you can see here that in this example, the change was because we did a receiver swap, and then there's a link to a change request, which ties back to what Sandeep was talking about yesterday, that within ServiceNow, we have more notes from the field service engineers about the visit. And also, so before any of these changes are applied, they go through a mandatory review by a network specialist. So on one hand, this helps to prevent any errors. So, for example, if the values are transposed or if we're missing a decimal place, for example. But also it gives the network specialists the opportunity to observe the trends of what's happening and instigate further investigations or perhaps put a site on a watch list. So after the changes have been approved by a network specialist, we then need to do a deployment to actually make the changes to the site configuration. So we use a release automation software called Excel Deploy, and this gives us full traceability of exactly what's been applied and exactly when it's been applied. And then also we have the ability to roll back changes quickly and easily, so we can always roll back to a good known state. So some of the challenges that I faced when doing this work. So again, if we look at the different services of Cyclops and then focus in on the receiver calibration GUI. So when I first started doing this work, I had everything in one big monolithic chunk of code, which I found quickly was very difficult to maintain and make any changes. So I had sort of one big module that was responsible for lots of different tasks within this GUI. And then as soon as you make any changes, you then got a knock-on effect elsewhere, which becomes quite difficult to hunt down the problems. So in a similar vein to what we do with microservice, the microservice approach in Cyclops, I've separated this down into smaller independent parts. So it's now following a model view controller design pattern. So this is a design pattern that's quite commonly used in GUIs. And it means that you've got complete separation of the model and the view. So the model contains anything that's related to the data. So the model will be storing the data, doing all the calculations, doing the verification, for example. The view is what the user interacts with. So the user is responding to the view. That's the visual representation of the GUI. And then the controller facilitates any communication across the application and acts as an interface in between the model and the view. So that was also something else that I found difficult, in that doing the interface to the analog to digital converter, because it's quite difficult to work with hardware sometimes. It took me a little bit longer to get the ADC interface working correctly. But one of the benefits of this design pattern is that I was able to replace this with a data simulator. So as long as the controller's getting the right data in the right format, it doesn't really care about what's actually contained in there. So you can simulate the data, and then further on down the line, I was then able to add in the ADC interface. So in terms of quality assurance, so we didn't have the benefit of a gradual changeover because we had a fixed deadline for the server upgrade. So this meant that we knew we would have to do a direct changeover, which comes with slightly more risk. So some of the quality assurance steps that we took. So first of all, the model view controller design pattern allows you to do more effective testing. So that means that you can quite extensively test that code before you actually put it into operation. We also did a full quantitative assessment, so comparing the old and the new process. So we used the same input data for both and then confirmed that all the calculations and plots, for example, were equivalent. We also incorporated user feedback throughout the development process. So very early on, I had a prototype of this work and held demos with the end users to try and capture their needs and requirements. And then finally, once it was finished, this went through user acceptance testing. So our end users, our field service engineers, tested this in a typical environment to check that it was fit for purpose. And so they were testing both the GUI itself and also any of the accompanying documentation. So in terms of future work, so some work that is planned is to calibrate at the actual site frequency instead of a nominal site frequency. So this is already implemented in code, but we want at least one calibration cycle where we're trying to minimize any other changes. So we'll do one calibration cycle using the nominal frequency, and then after that, we'll start switching to doing it at the site frequency. We also plan on revisiting the verification thresholds to make sure that the fails are meaningful and that anything that fails is something that actually requires action. So something that's planned but is currently blocked would be to add an interface to control the test signal generator. So this is another benefit of this design pattern in that you can very easily add another interface to control the test signal generator here. So the controller is already aware of exactly what parameters it needs from the test signal generator. So it would just be a case of adding the interface for the controller to control. And if we did that, then beyond the actual physical cable connections, that would fully automate the process. So that's something that's currently blocked by hardware issues. And another thing we'd like to do is do some automatic monitoring for trend analysis. So we currently do create manual plots for trend analysis, but it would be useful if we could get that done automatically to get some automatic monitoring. So in summary, so this has been a significant improvement on the previous process. So since it's 4 times faster, we've been able to implement an additional calibration, which will hopefully identify issues with the TR cell or the waveguide. There's also plenty of opportunity for further improvements, and the way it's been designed, it's quite easy to implement these improvements. The software tools that we use give us full traceability, so using Git for version control and XL deploy for the deployments. And this has shown that this sort of GUI is possible with just the Python standard library and a few basic dependencies. And I think my biggest takeaway from this has been that following good software design principles makes it a lot easier to maintain an application like this and also implement new features. Thank you for listening. Does anyone have any questions?
Thank you. Your dynamic range looks super good. And my question is, if you can brought one of your, it seems you didn't go to the 1 dB compression point. It seems that you talked earlier in the upper part. So similar, and then my question is how large is the dynamic range, and if you have used the two channels to reach such a wide range, and at what level more or less you do the transition from one channel to the other, to the low to the high system.
So we have a 90 dB dynamic range, and that's just on one channel. We don't do a high and low split. I think at the top here, so we did previously go a little bit further, but we found it was starting to approach saturation. So we've restricted that a little bit at the higher power levels.
Breaking down monolithic application, not be controlled. I totally agree with you that maintaining monolithic application can be a nightmare. I just wanted to suggest that when you move forward and try to implement automatic monitoring, you might be interested in use Grafana and FlexiBit. As I mentioned that yesterday, I believe I saw that also on my browser. We are using that in Argentina. This is open source software. We have support from the community. It's working fine. That's a recommendation.
Yeah, thank you. Yeah, I think we do have plans to look at Elasticsearch and Kibana for the sort of dashboards. I think within the Met Office, we've got a sort of centralized login system. But yeah, I definitely think a dashboard of that, something like that would definitely be beneficial. Thank you.
Is it in the waveguide corrosion? Is it failure or location based?
So this particular example was the a failure in the dehydrator. So yeah, it caused quite a significant amount of corrosion. And I think it was a joint that had a higher probability of galvanic corrosion as well. So that really accelerated that.
So, you said that you're using like traditional signal generators in calibration. Do you have a site-specific signal generators for all sites, or do you carry them around, and how often do you calibrate actually the signal generators?
Yes, the testing generators, so they will be with each service centre. So our field service engineers would carry them to site. And they're calibrated on the manufacturer's schedule, which I think is every 3 years.